Hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have, hi, my name is Brody Holm,
I'm Connor Holloway.
I'm James McCrum.
and this is Project 1. We decided to do the billiard ball problem. So, for our description, we have known information as well as stated tasks. First of all, our provided info is a billiard ball with a known mass M is struck with a force F known as Fs. That is parallel to the table and applied by a Q for a known time delta T, and that the force of friction on the ball is smaller than the force applied by the Q. Our first task is to find at what point the billiard ball can be struck so that it rolls without sliding on the table and find out how fast it is rolling. And our second task is to find out if the ball was struck in the center as well as parallel to the table. Find out how far it slips without rolling and describe its rotational and translational motions. And now we have our free body diagrams. So for our free body diagrams, they are representing the pull cue and the ball, and the variables are the height of which the cue strikes the ball along the ball's mass and radius, which the radius and mass are constants here, and h is unknown. And for the other free body diagram, it is representing the cue ball after it has been struck, which is representing forces of gravity, normal force, strike force, and force of friction, as well as angular velocity circling the ball. Now, for understanding the problem, we have some given values and we have our general questions and assumptions. So starting with the given values, we have mass, which is known as M, time struck, which is delta T, strike force, which is Fs, direction hit, which is parallel, and we have static and kinetic friction coefficients. And our general questions ask us to find the location of strike on the ball and how fast it travels, and the distance the ball travels before rolling without slipping when struck in the center. And our assumptions are that the billiard ball has a constant mass density, i.e., our moment of inertia would be 2/5 mr squared, and that it will roll on a flat surface, as well as there is, well, air resistance is neglected in this case. Now on to laws, equations, relationships, and important values. These are all of our laws, and we will be using these throughout the project. Obviously, there is a lot that have been listed here, so we won't name them here, but they will all be mentioned later on.
This part of the question, we first needed to find the equations that would fit with the problem. Using Newton's second law, we were able to combine and rearrange the equation P equals mv and F equals mx times delta V over delta T into P equals F times delta T. Having this in terms that are known variables, we substitute it back into the equation to get V equals the force of the strike times delta T over M. Using the internet, we found that the moment of the inertia for a sphere is 2/5 mr squared, which we used in the equation L equals I times W. To get momentum, W, in terms that we know, we use the torque equation of torque of strike times delta T equals delta L, which simplifies to the force of the strike times H times R, which is the height that we want to hit the ball at in terms of the radius, times delta T equals I omega F, or omega final minus omega initial. which is 0. We want omega, so the equation omega equals force of strike times h minus r times delta t over I times m, or what is written on the board there comes into play. From here, we can finally use the equation v equals omega r, which is the conditions for the ball rolling without slipping. Most of this just kind of cancels out, and it leaves us with h equals 7r over 5. We did a special case analysis for this in which r is very large, so the ball is huge, which any increase in r leads to a increase in the height in which we strike the ball, which generally does make sense. And if r is 0, then the height at which we strike the ball is also 0 because it doesn't exist, which still makes sense. We also did a unit check for this, and since the height of the ball is measured in meters and r is also measured in meters, it balances out and everything makes sense.
All right, moving on to part A2, where we solve for how fast this ball will roll. And what is nice about this is that we have already solved the first part of this problem, being that we had to use the speed formula V is equal to strike force multiplied by the change in time all over m. And we used that to find the height previously. And since we are looking for angular velocity now, we can write that as V is equal to angular velocity multiplied by radius. And putting everything in terms of W changes the problem to be omega equals strike force times delta t over mass times radius. And that is our angular velocity formula. And for our unit check for this, it is fairly simple. Omega itself is radians over seconds, and everything else in terms of omega is kilogram meters per second squared times seconds over meters and kilograms, which after a lot of canceling out, meters goes away, kilograms goes away, and one of the seconds goes away, which just leaves us with radians per second is equal to radians per second.
Part B of this problem, we are looking at a different scenario. What if the ball was struck in the center, the cue still being parallel to the table? How far does it go? What's the change in x before it is rolling without slipping? Now here we have 4 steps. Before the 4 steps, we have a setup. So we know that the ball starts at rest. So we know that the initial angular velocity is equal to 0. And in the last part, we found the linear velocity, which is v equals the force of the strike times the change in time over mass. Lastly, we have that the force of friction is equal to mu times m times g, and we get the m times g from the normal force. Alrighty, step 1, define velocity from the kinematics equations. For this, we'll be using v equals v initial plus acceleration times time. And we can use Newton's second law that the force net equals ma to solve for a, acceleration. And doing this, we get things to cancel out. We get m to cancel out, so we get a is equal to mu times g, which is perfect. And now we have everything that we need to solve for velocity. So just by plugging everything in to the first kinematics equation I just mentioned, we get velocity equals the force of the strike times the change in time over m minus mu times gravity times time. Alrighty, in step 2, we are going to find the angular acceleration alpha. To find the angular acceleration, we can relate torque and alpha through Newton's second law again, but this time for rotational motion, which is torque net is equal to moment of inertia times alpha. And we know from the previous step or part that the moment of inertia of a solid sphere is 2/5 mr squared. And so through some rearranging in algebra, we get that alpha is equal to 5 mu g over 2r. Which is good because now we can take alpha to find omega through another kinematics equation, which is, if you follow the arrow, going to be up on the top right. Like the last, this is omega equals omega initial plus alpha times time. And since we know that omega initial is equal to 0, we get that omega equals alpha times time, which equates to 5 mu g over 2r all times time. In step 3, we will relate velocity and omega, the angular velocity. And so now that we have this velocity, and angular acceleration, we can finally solve for time. To do so, we will relate velocity and angular velocity through the equation v equals w cross r, a cross product. This is essentially v equals the magnitude of w times the magnitude of r times sine of theta. Since theta in this case is 90 degrees, sine of theta equals 1, we can neglect sine of theta. So we get the force of the strike times the change in time over m is equal to, or minus mu gt is equal to 5 mu gt over 2r all times r. Through some more algebra manipulation, we get t is equal to 2 force of the strike times the change in t over 7 mu g. In step 4, we can put it all together and solve for the change in position. And now that we've solved for all the other unknowns, we can finally solve for it. We will use the last kinematics equation on the top right, velocity final squared equals velocity initial squared plus 2 acceleration times change in position. Now plugging everything in, we get 5 over 2 times mu gt squared equals the force of the strike times the change in time over m squared minus 2 mu g times delta x. Again, we're solving for delta x here, so through some more algebra, we can arrive with an equation delta x equals 12 over 49 mu g times the force of the strike times the change in time over m squared. This is, of course, the distance that the ball will travel before rolling without slipping if struck dead center by the cue. Now we have some sense making for part B, some special case analysis. So for the first one, we are looking at what if m increases. More specifically, what if mass goes to infinity? Since mass is in the denominator of the force of the strike times change in time over m squared, an exponential quantity, the more the m increases, the smaller change in position we'll get. So as m goes to infinity, the change in position will go to 0, as you can't move something with infinite mass. So this makes sense. Second, we have what if the pool table was on Mars? We know that Earth's gravity is equal to 10 meters per second squared, and Mars is about 4 meters per second squared. This means that a cue ball struck on Mars will have greater displacement than the ball on Earth. Since all other variables are the same, we can simply represent this as a comparison of fractions, where we get Earth is 12 over 490, and Mars is 12 over 396. And so clearly we can see that Mars is a greater fraction, and so Mars will have more change in position than Earth would, which makes sense. Finally, we have a unit check for this. We get delta x, which is equal to meters, and through a lot of cancellation of kilograms and seconds through that equation on the right, we end up with just meters, which is perfect. Reflecting back on what happened through this problem and the first 5 weeks of Physics 212, we can see that it relates to most of the things we've covered so far. This includes angular velocity, angular acceleration, momentum, angular kinematics equations, and their linear counterparts from 211. Although we have yet to see a complicated problem like this in lecture, lab, or studio, we have seen all of its individual components represented in their own systems. More specifically, problems like calculating the angular velocity of disks spinning, or momentum problems from homework 4. So taking what we know from those individual systems, we linked together the equations in a way that allowed us to find velocity, height, and change in position. Or momentum problems from homework 4. So taking what we know from those individual systems, we linked together the equations in a way that allowed us to find velocity, height, and change in position.